Welcome to this video on angular momentum, part 1. In this video, our main objective is going to be to come up with a rotational analog for linear momentum and to look at it from the perspective of planetary motion. So we'll also end up developing some of Kepler's laws of motion in the same video. So let's jump right into it by looking at this image here. Here we have the Earth, and we have the Sun, and we have the planetary orbit path or orbital path of the Earth. Now there are two important things to note here. First of all, this image is not drawn to scale because the Earth is many magnitudes smaller than the Sun, which here is not shown. Also, the Earth's orbital path is not as elliptical or oval-shaped as this. I've done this to exaggerate the fact that it's not a purely circular orbit, which is true for most of the planets. And that's going to become very important in a few minutes. The first thing we want to do is to take a look back at linear momentum, because that's something that we already know. And after all of the ways that we've converted old linear mechanics concepts to rotational mechanics concepts have involved looking back. So we know that P stands for linear momentum, and linear momentum is the product of mass times velocity. We know that the units for this are the kilogram meter per second, and that the rate of change of the momentum, so in other words, if something's momentum changes, the speed at which that momentum changes is equal to the amount of net force that is acting on that particular object. This, of course, has units of kilogram meters per second, or kilogram meters per second squared, which we know as a Newton. So that's going to become very important for us as we develop our angular momentum rule. So just like we did with many other mechanics concepts when we were converting them, a lot of them had to do with multiplying the angular component by r, or dividing the linear component by r, the radius path, the radial distance of the circular path. For instance, we know that v, linear velocity, is equal to r times angular velocity. We also know that linear acceleration is equal to r times angular acceleration. So that would lead us to believe that linear momentum times r should leave us with angular momentum, which is uppercase L. And that is true. The only thing that we need to adjust here is that because of the nature of angular momentum, which we'll get into in the next few videos, this is actually a cross product, P cross R. Another way to expand that would be to say the linear momentum, which is m times v cross r, would show us a fully expanded form to calculate the angular momentum. We'll get to the units for that in a little bit. So something we want to look at here is that because this is a cross product, when we're calculating the angular momentum, we have to make sure to multiply the two by the sine of the angle between them, as we're going to see pretty soon. Now we're going to jump over to our planetary motion model. And what we're going to be doing here is establishing Kepler's laws of planetary motion indirectly. The first is what we saw here, is that orbits are elliptical. Now that means that their paths are a little bit of a squashed circle. The fact that orbits are elliptical means that the Sun isn't at the center of the orbit, but at one of the focus points of the ellipse. If you've forgotten the geometry of an ellipse, you want to go check that out because it is kind of important in understanding this. But the main things to remember is that an ellipse has two foci, and its path is a bit of a squashed circle, adding up any of these combinations. So if you were to draw A and B like this, it would always add up to the same value, much the same as the radius of a circle would always remain constant. but we'll get back to that later. So as we see here, the Earth travels around the Sun, and at some points we could say that the Earth is going to be closer to the Sun, and at some points it's going to be farther away or further away from the Sun. And the observational data shows us the following information. It shows us that when the Earth is closer to the Sun, the velocity when it's closer is greater than the velocity when it's further away. So what we can write here is that the velocity when the Earth is closer is greater than the velocity when the Earth is further away. That's all from observational data. That leads us to the understanding that when the planet or the orbiting satellite is closer, we'll call that value RC, it has a value of VC. And when that satellite is further away, we'll call that RF for further, we know that its velocity will be less. So there's an inverse proportion between the distance you are away and the speed you're traveling. That means that the kinetic energy when you're closer is greater than the kinetic energy when you're further away. Now, if we think of closed systems as having conserved energy or having constant amounts of total energy, that would imply that the gravitational potential when you're closer is less than the gravitational potential when you're further away. And that actually makes sense if you think about the fact that you're closer to the planet, you have a lower potential energy. So your height off the planet, or off the Sun in this case, would be less. This leads us to Kepler's second law, and his second law basically states that the time that it takes for a planet to go from one position to another position in an equal amount of time when it's closer, so going from A to B here versus A to B here, it will actually map out the same amount of area as it would at any point. That implies that it must be moving faster. So we could say here that planets or satellite objects, planets move faster when closer to the Sun. Now, of course, this works with other rotating objects as well, not just the Sun and the Earth. So that's pretty interesting. So we can see here that when R is less, V is more. That's what we observe. And that implies that at any point, the angular momentum is constant for an orbit. So we actually see the angular momentum being conserved within the orbital path, which is very, very interesting. Now, the last thing we'll end this video with is comparing this rate of change of linear momentum to the rate of change of angular momentum. So angular momentum we know is L, so we'd say delta L over delta T is going to give us not net force, but net torque. And that will be something that we will develop a little bit more in the next video.